big. All right, so bivariate analysis, guys, just means you're comparing two variables. Okay, so if I was highlighting bivariate, okay, bivariate analysis is concerned with the relationship between pairs of variables, and that should be X and Y. X, Y. Okay? The way that we display those is known as a scatter plot. Okay? The relationship or between these variables is referred to as correlation. All right, so we can use we use their correlation to allow us to make predictions about the value of one variable based on the other. The stronger the correlation, the more confident we can be of our prediction. All right, so you have to be careful between what is meant by correlation and causation. Okay, whereas there could be a correlation between something and not necessarily a causation. So I'll give you, we'll get to that in just a second. All right, so to make a scatter plot, I think you've all done scatter plots. Okay, so your independent variable, your X, okay, that goes on your horizontal axis. This is your X value, and then your dependent variable, which is your Y, okay, goes on the vertical axis. All right, now, the different types of correlations that you have. You can have a positive correlation, all right? That means you got if we were to draw a line on this thing, the line would have a positive slope. Okay, this would have a negative slope. Okay, so positive correlation means as one variable increases, so does the other. Okay, that's what positive is talking about. As X increases, Y increases. Whereas a negative correlation, as X increases, Y decreases. There's a decrease as we move to the right, whereas on the other one, there was an increase as we move to the right. Okay, and then you can have no correlation. Okay, where the correlation is close to 0. So if there's no clear trend in the data, there's no correlation between the two. Okay, so to give you an example between correlation and causation. Okay, just for example, if I put shoe size and vocabulary, okay, now chances are if we plotted people's shoe size, okay? And the breadth or the depth of the vocabulary, okay, if you did that, you know, for each of your years, your shoe size and somehow you tested your vocabulary, it could appear that there's a positive correlation between the two, okay? Now, we know that shoe size does not cause an increase in vocabulary, all right? So even though there's a positive correlation between the two, that doesn't necessarily mean that one causes the other to occur. All right? Because chances are, as you get older, your shoe gets bigger, all right? And your vocabulary increases because you're older. So really, the causation is age in vocabulary, not shoe size in vocabulary. Even though it would be true to say there's a positive correlation between shoe size and vocabulary, not necessarily a causation between shoe size and vocabulary. Really, what's causing it is age. Okay? All right. So, there's different strengths of correlations, okay? So, the tighter the dots are to a line, the stronger the correlation. All right? So, you have positive and negative correlation, and then you also have strength of correlation. Okay? So, the stronger the correlation, the more we can trust the prediction based on it. Okay? So, in a strong correlation, the data is closely approximates a line. That data is pretty well grouped around that line. Now, as the data starts to spread out a little bit, then your correlation loses strength. So this would be considered moderate correlation. Okay, the data values loosely approximate a line. So you're not going to be as confident in your prediction. Now, when we start doing this in a few minutes on our calculators, there's R values that determine these things. Okay? The R value, well, we'll get to it here in a minute. All right? So this, even though this is still a positive correlation, it's pretty weak because the data points are relatively far. If we were to sketch a line that kind of equally, you know, you have as many dots on top as you do on the bottom, but they're fairly spread out from the line, then that's demonstrating a weak correlation, which would mean you wouldn't have much faith in your prediction. Now, in a few minutes, we'll be calculating a value that tells you how strong the correlation is. And that's called the correlation coefficient. Okay? So you're not trying to decide if it's strong, moderate, or weak. The R value will tell you that. Okay? All right. So you can have, what we're mainly going to be dealing with are linear trends. Okay, so you got a trend here that you could draw, you could fit with a line. That would be a linear trend. Okay, you could have trends that are exponential. You could have trends that are logarithmic. Okay, you could have trends that are cyclical, like sine and cosine. So, okay, that would be, in this case, this would be logarithmic. like this one right here, or you could have trends that are exponential. Means they look like this, or this. Okay, you could have trends that are cyclic. Okay. And then you could have trends that are logarithmic. All right, so if we were doing a scatter plot, now your calculator does scatter plots. You just put these in as L1, L2, and you choose scatter plot. Okay, so we'll just do it on our calculator. Well, let's just do it by hand. It doesn't take very long. We're going to do them on your calculator anyways. Okay, so X, Y, and now we just plot these points. 1, 1, 2, 3, 3, 3, 4, 5, 1, 2, 3, 4, 4, 6, 6, 7, 1, 2, 3, 4, 5, 6, 7, 6, 5. Okay, 6, 5, 6, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10. So 8, 9. So something like that. Okay, and then we're going to sketch a line. Okay. Yeah, I mean, if you're off 1 or 2, guys, it doesn't matter right now. But you can see here that we've got a linear relationship. Okay, how would you characterize, you have a positive correlation. How would you characterize the strength of the correlation? Strong, medium, weak?
Moderate.
Yeah, probably moderate to strong. Okay, so linear, and then the strength is, we'd probably say, is moderate to strong.
Oh, yeah.
Okay, all right, now these lines that we're drawing, guys, that's referred to as a line of best fit. And initially, you're just eyeballing it.
But isn't there
Yes, there's a way to calculate one, yes. Okay, now this line of best fit is also referred to as a regression line. So there's all types of regression, guys. There's linear regression, there's exponential regression, there's logarithmic regression. When you're trying to fit a curve to a collection of data, that process is called regression. Okay, so a line of regression or a line of best fit shows the trend and the direction in a scatter plot. Okay, and then the better it fits, the better our prediction. All right, now, if you're just doing one by eyeballing it, okay, so we typically start by drawing the line of best fit by eyeing it. And what you want to try to do, like I said, you want to get an equal number of data points above the line as there are below. Now, we can improve this line by giving ourselves a reference point through which to draw the line. So a good reference point is the mean. Okay, so the mean point is going to be the average of the, you're going to do the mean of the independent variable and the mean of the dependent variable. Okay, so if I was going to do this data here, okay, and I want to find the mean value, I'm going to do the average of the fat content, and then I'm going to do the average of the calories. So the mean point is simply finding the average of the total fat. That's going to be your x-coordinate. And then the average of your calories, that's going to be your y-coordinate for the mean point. You're just doing the average of each list. That's your x and your y. Okay, so when you draw your line of best fit, you want it to go through those points. All right, so find the average of fat. So what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 items. And someone else, let's see. Eddie, you do the average of the calories, please. And Corey or Logan, do the average of the fat. You're dividing by 11 on both.
Yeah, I'm pretty good in the lists, so just give it some more.
Yeah, you could put it both in the lists and then just do your one variable statistics to it. Yep. And what did we end up getting?
I got 457.27.
22? 22.45. So we'll say roughly 22.5. And what was the other one? 457.3. So we'll say 457. All right, so we would plot that. Okay, so if we were going to graph these, okay, what would you use as a scale? So this would be your calories. Okay, this is going to be the total fat grams. This is total, where'd you go? Calories. Okay, now you just got to figure out how to divvy that up. Fat's got to go up to at least 35. So maybe count by fives, 5, 10, 15, 20, 25, 30, 35.
Oh, I didn't even have that.
Okay, we got to get up to at least 600 calories, so what would you do for that? What would you count by? 50? Okay. Okay, and now it's just a matter of plotting and seeing what we get. Okay, so let's see, 560, 550, 34, 590, 500, 28, 560, 440, 300. All right, so we can see there, it looks like there's a positive correlation. Okay, now we're going to plot our mean point. Okay, 22,457, 22,450. And so when you draw your line of best fit, you want it to go through that. So maybe something like that, where you're trying to have as many points above as you do below. So that's roughly close. So the problem with doing this is we all could have different lines of regression. Okay, now if we wanted to write an equation for this line, yeah, find the slope, find the y-intercept, and you could come up with an equation for it. So this is our line of regression. Okay, we could say roughly, let's see, y equals mx plus b. Okay, b looks like it's, I don't know, maybe 230. Okay, now calculate the slope. So my slope looks like it's 1 up, 1 right, which is really 50 up and 5 right. So my slope is a change in 50 over a change in 5, which is around 10. So that's like just a rough, if we got the fat content of something, we could use that to predict what the total calories are by multiplying it by 10 and adding 230. And just from that line, you probably have a fairly strong confidence in your prediction. It's a fairly good fit. Okay, so what does it mean if the y-intercept is at 20? What's that telling you? How would you interpret that?
That's the lowest time then. So that's the,
How old are they?
that's, 70.
How old?
7.
So,
Why do you say 7?
Because it says that the data would be 7 weeks.
Right, okay. So this would actually represent an age of 7. Okay, all right. So we would predict that it takes, at age 7, takes 20 minutes to run 1 kilometer. Okay, all right. Now the slope is -1 over 2. Okay, so what's that telling you?
as the age, so it takes less time to run.
Okay, how specifically, what's,
By,
Every year they decrease it, really kind of half a minute off of the time.
right, so every year a half a minute off their time, or their time decreases by 1, as their age increases by 2 years, time decreases by 1 minute? Okay, or better yet, if you did it per year, okay, so every year their time improves, or they get a half a minute faster. I mean, there's lots of ways you could write it. 1 minute.
Every year it would be calculated.
Yeah, oh yeah, you're right. Gets half of a minute faster. Or their time improves by half a minute, however you want to write it. Okay, now, there's a limit to that, because obviously, if you kept drawing this line, at some point their time would be 0.
Yeah.
Okay, which is not real.
It would just be a non-linear.
Okay, right. Well, it's like that wouldn't make sense anymore. Someone doesn't run a kilometer in 0 seconds when they turn 20, or when they turn a certain age. Okay. All right. Okay, so the word gradient, when you see the word gradient, that's referring to slope, and it's referring to the amount the y increases when the x increases by 1. Okay, so now we're going to use the equation to find, or we're going to use our calculators to get the line of best fit. Okay, and let's see, we only got a couple minutes, so we'll just stop there and we'll pick